Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question, raw and uncut. So we have a medium today, some more graph problems. So it's called number of ways to arrive at destination. So you're in a city that has n intersections. So I'm guessing they are the nodes and bidirectional roads. So undirected. I see the bounds. Actually, we have very small bounds. So, the number of nodes is only 200. The number of edges, which are roads, are, um, well, like it could be a complete graph. So, I don't know exactly a number, but actually I'll calculate now. So it's like 201 times 200 divided by 2. Okay, so it's around like 20k roads at most. And then we have like some time here. There's at least there's at most one road connecting any two intersections. Okay, so like you wouldn't have multiple edges, and you can reach any destination from any other intersection. You can reach any intersection from any other intersection. Right, so that means the graph is connected. So it's one connected component. Let's see. So you're also given an integer n. Okay, so that's what we have already. So roads would be the edges, and that would be the two intersections, and time would be like the weight, I'm guessing. You want to know how many ways you can travel from intersection 0 to intersection n-1 in the shortest amount of time. So you want to return the number of ways you can arrive at your destination in the shortest amount of time. The answer could be large, so you want to return modulo of that. Yeah. One thing I noticed with this question is that the acceptance rate is pretty low, so there could be a lot of edge cases. But yeah, let's think about how we can approach this. So okay, so the first thing we definitely should do is yeah, we should find out maybe, well, because we know that we want to go from 0 to n-1. So like if we look at this example, well, that means we want to go from 0 to 6, right? So should we find out the shortest time first, maybe? So what is the shortest time here? Well, it says 7 minutes, and then yeah, let me think about how to do this. So the shortest amount of time. Yeah, so it could be like some graph DP as well, where we store the number of ways to like get somewhere. Let's see. Yeah, also we okay, yeah, another observation is let's say we can let's say we can get to a node in two different times, right? So if I draw it out, so if we have something like this, I don't know, we can have this and then that, right? Let's say we have something like this. If we can get to 1 at time equals 1, that means we definitely wouldn't use like this path here, like the 2 and 2, because if the time is minimal, but this is obviously not minimal to get to the same node, we will never use something like that. So yeah, so let's say for like let's say for 6, like let's say for the final node, like we know the time we have to spend now. We can first go to its neighbors, and we also store like the we also have to store the minimum. Well, we also have to store the shortest time to get to each of its neighbors. Yeah, so we can kind of like DFS back out, I guess, or BFS. Um, yeah, but how do we calculate the number of ways? Like we need some ways to store that, right? Um, yeah. So for example, like 5, we know we can get there, in 6. Yeah. How do we store that though? Um. Yeah, and it is saying that like it could be very large. So that's kind of what's worrying me as well. Cause yeah, it could be very large. Um. Okay. Well. Yeah, but it could be some DP, of course. Um. What if we store the number of ways to get to each node in its minimal time? Would that help? Um. Yeah, like as I said here, like like my observation here is that if you can get to a node in different times, you only want the minimal time. So what if we start at 0, um, and then I guess we can like just we can run a Daishra. So um, so when you run Daishra, it always gives you the like you always go to the minimal time, right? So I'm not going to explain Daishra too much, but like it will give you the shortest path. So if we look at example 1, 0 is going to go to 1, um, and then it is going to add 3 and 2 in. Wait, but yeah, I think maybe Daishra will work. So when we get from 0 to 1, we know that the minimal for 1 is 2. So if we have any more ways that gets there, well, um, like in time 2, we can like add that number of ways, right? And then yeah, so I'm thinking of like something like 5. So um, so what do we have here? Well, we have so 1, 2, 3. So we can get here at time 5. We can also get here at time 5. Let's ignore 4 for now. Yeah. So technically, like 0 is going to go to 4. So the order is going to be like something like 1, 3, 2, and then 4. And then after that, we'll look at time 6, which is 5, right? But when we are adding it into the heap, we are going to add 2 things here. So that means there are 2 ways to actually like get to this node. There's one way to get to this node in minimal time. There's one way to get here. So that makes 4. I think that works. Am I confident though? Yeah, I think like with the minimal time thing, it proves that my algorithm works. Hopefully it doesn't backfire. I'm like 90% sure it works. But yeah, let's try to code it out first, maybe. Okay. So what do we have? We have the minimal time for each of the nodes, and also it is guaranteed that like they're connected. So it doesn't matter. Oh yeah. Another thing to observe is let's say this edge, so like this time 7 edge. Let's say it is actually 1. So that means we can get from 0 to 6 in time 1, right? Like in Daishra, it doesn't matter like for the other edges, right? Because like we found the minimal time here, and well, we don't have to you know, like we don't have to check the other ones because the other ones are definitely slower. We only want to find the number of ways we can travel to get to the destination in the shortest amount of time. Okay. So yeah, we have float infinity, so that will be the minimum time for. So we want to set that first, and then we want to set number of ways. So we'll set all of them as 0 for now. But then actually, for the 0th node, we have to set it as 1, so we can add it to the other ones. Okay. And then I think we need a scene array for Daishra. And then we can do Daishra here. Do we need to? Yeah, do we need yeah, I don't think we need a function. Just do Daishra like this. Yeah, because we're using a heap, so we're using a min queue to keep getting the shortest time, right? So let's have a min heap. So that means we have to import heap queue. We will call it. Wait, we're calling it heap already. Yeah, we just do that, and then here we are going to just mark what the elements are going to look like. So it's going to be time and then the node. So yeah, we can do while true because we are guaranteed that we will reach the final node eventually. So yeah, the first thing we have to add is wait, heap queue dot. I'm just gonna import them, so I don't have to type heap queue every single time. Okay. So we want to do heap push. So heap. What do we want to push in it? We want to push 0 0. So the first 0 means like 0 time. The second means well, the node, because we are starting at 0, right? Okay. So we want to do heap pop for the heap, and we are going to get time and node. So if node is seen, we just want to continue. Wait, actually, do we want to continue in this case? Yeah, because of something like 5, right? When you get there in another path. So I think like we actually have to do something special here instead of just continuing. So we have to yeah, so I think what we should do is if for the current path the time like it, so like let's say we go like 1 3 first, right? And then we go to 5. So so that's gonna tell us that to get to 5 our shortest time is 6. But then when we are using this path, we also have a time of 6. So we have to add 1 to the number of ways there. Well, actually it should be adding 1 to the number of ways to get to the wait. Yeah, we want to add the number of ways to get to the previous node, actually. Yeah, wait, so in that case, maybe you have to store the previous node as well, right? Yeah, I think we have to store the previous node as well, in that case. Or can we just pass it on? No, we cannot just pass it on, because like, well, if we just pass it on, when we get here, we're gonna get, well, like we're gonna get like number of ways like to be 1 here, but actually it is 2. So like we want the most updated version when we actually get to like the next node, right? So 0 0. Yeah, what should we do for this one? I guess we can do -1. So um yeah, we can do prev here. So if the mean time for prev is equal to time, okay, we have a placeholder at the end. Wait, actually, I don't think it matters. Like for, well, this is not very good code, but if you look at, well, if this is -1, the minimum time is infinity, right? Wait, wait, but the minimum time. Oh, but the node is not seen yet, so we never really have to deal with that, I think. Yeah, I think so. Yeah, so if mean time of previous. Wait. So if it is seen, we will have know the mean time. So we actually want the current node's time. So if it is equal to time, that means we found another way. So that means the number of ways for the current node, we have to add the number of ways of the previous node that it is coming from. And that actually wouldn't matter because we wouldn't have gotten to the last node yet. Like when we first see, well, 0, or like if we're going back as well. Yeah, actually, when we go back, it's going to be longer than, like it's definitely going to be longer than, well, like time 0, right? Like when we initially start out. So yeah, I don't think we have to worry about that. We can just set it as -1 and it should be fine, unless it isn't. Right. So if it is seen, we do that. So otherwise it is not seen. So we'll set that to be true. Yeah. Okay. So when we set it to be true, we also want to set the minimum time. We also want to set the minimum time to be time because, like, because of how dice works, basically. Yeah. So that means we're gonna set time here, and then the number of ways. We also have one way to get there now. So we are having 0 here because, like, just because we don't want like any edge cases to like make something wrong. So we'll update it here. Like it makes the most logical sense to do that. And now for next in. Oh, we have to process the roads as well. Okay, yeah, let's just make it a JSON list then. So JSON list, and then now for ABT in roads, so JSON list, append. So we'll have the time after. Yeah, so we can do something like this, and then here we can just do a JSON list node. Yeah, so for next in a JSON list node, so let's say we start off at 0, we want to go to each of these and we don't want to not add it in just because it is seen because of something like 5, right? Yeah, so we can do actually, is that true? So if 5 is seen, wait, but that means it would have, if 5, like when 5 is seen and if there are more like minimal paths, that means that path should have been processed first. So yeah, actually, if a node is seen, we actually don't want to get to it. So if next is seen, just don't want to do anything with it. And then so we want to add it in, right? How do we do that? We can just heap push. So heap, and then so we have the time. So it will be the current time plus. We need the time as well here, of course. So it will be time plus t, and then oops, we should put it in here actually. And then we have the current node, and then we have the previous node, which is node. So we just keep looping through like that. That's gonna give us. That's just gonna be a Dijkstra part. But then when we actually get to, the last node, I think that's when it is a bit trickier, I guess. Yeah, where should we check it? Let's check it. Check it here maybe. So if node is equal to n minus 1, so that means we have reached the final node. I think we're just going to continue here. So we don't want to get into the logic below. If the node is seen before, and wait, so if we have seen the node before, and if we have reached, like if the time is no longer minimal, that means we have found all the paths already, right? So we don't need to we don't need to keep looking. So if it is not equal to time, so like I don't know, like let's say we have found all the path 7, and then there's like 0, 1, 2, 5, 3, 6, a path like that, right? So that's gonna be cost 10. So if we reach that, that means like because of Dijkstra, that means we have reached we have passed all the time 7 paths. So we can just return the answer now. So we can return I think it's number of ways of node, because node is the last node now. And otherwise, another case is if it is seen, but the minimum time, but if it is equal, just technically I don't need the second condition here, but I'll just make it easier to logic with. I'll just do that. So if it is seen and the minimum time is that, that's good news. We found more paths. So number of ways for node, we want to add the number of ways from the to get to the previous node. The last case is if it is not seen, right? So if we haven't seen the node yet, that means seen node. That means we want to add. Wait, actually, do we even have to continue here? Can't we just let these things happen? I think we can, yeah. So it's gonna set time, and then it's just gonna set number of ways as. Wait, actually, number of ways shouldn't be one here. Yeah, number of ways should be the number of ways to go to the previous node here as well. Because let's say 5 going to 6, right? Like if this is the first thing we do, it will have 2 paths to get here optimally already, and then we can get there, right? So there are already 2 paths, not 1 path. So we need the number of ways of previous. Yeah, and then we don't need to continue here actually. It's only if we have seen the node that we actually want to do that. Wait, do we even have to do this? I don't think we do. Yeah, cause it would have been done here. And well, if the minimum time is greater than time, it wouldn't do anything here. Oh wait, but then I have to continue here. Wait, why do I have to continue here? Yeah, don't I want to add more edges anyways? Like even if it is seen. Oh yeah, technically I don't need to add more in there. But I think maybe we should put this case up here. So if node is equal to n-1, and yeah, so we can do our checking up here, and then we continue. Right? Oh wait, the question is, do we actually need continue here? So if the node is seen, so let's say it is 5, it's going to check that, and yeah, it does add more number of ways there. Yeah, and then so if node, yeah, so if this is true, that means we reach the end. Yeah, so we can ignore this case for now. Let's think about this case. Yeah, I guess we do want to continue because we don't want to add like we have already added like 5 to 6 into the heap, right? So we don't want to add that again. So yeah, I do think continue here makes sense. Yeah, and we don't really need to do these stuff anymore if we have seen it already before. I hope it works. Oh, oops, what did I do wrong? Where is it? So heap pop of heap. Wait, index out of range. Is it because heap is empty? Okay, let's print the length of heap before we return the error. Yeah, it does have. Maybe I'm not adding all the things incorrectly, maybe. I should have. Huh. Now I'm a tiny bit confused. So heap push here. So if it is seen, we want to continue, right? But it should have pushed like 3 things here, right? Or is it the same? Oh, it's this test. So when you have like only one thing. Wait, but that means maybe we should set it to like while heap. So if it is empty, that means we have gone through all the paths, and we just want to return number of ways of n minus 1, right? Not right. Yeah, why is 0 here though? That means it is not actually like passing the things incorrectly. So we have number of ways here. We set it as 1. So scene node is true. Meantime, well, we set it as 0. Number of ways of previous. Yeah. So actually here we should do, if node is not equal to 0, we want to do this. Maybe we can use pref. So pref is not equal to -1. We can just do that. Otherwise, we actually want to set that to be 1, because like for the 0 case. Yeah, because 0 got set to 0 now, like the number of ways. Oh yeah, I forgot to do mod. What is it? Yeah, we need to do modulo of that. So that's not a big problem. We just do this. And then so for all the number of ways, we just want to do modulo mod. So whenever we are adding, we need to do that. But is that all? Yeah, are there any more like adding to number of ways? I don't think so. Okay, let me add this test case in just to make sure my modulo thing is working. Yeah, okay. Yeah, I hope that's the only thing I forgot. Okay, yeah. Yeah, it is the only thing I forgot. Yeah, well, this is a graph problem. As I've said before, it's one of my weakest things, like graphs. So, yeah, but we did manage to solve it. I guess this question is like, I don't know, maybe you guys find it very simple, but I would say this is like a hard medium. But yeah, thanks for watching. And yeah, before we go, well, I do have like some ideas on like what other content I can make. But honestly, if you guys have any idea, you guys should just comment below. You have made it this far, and I promise you, if you made a comment, I'll try to do whatever you guys want to. So yeah, thanks for watching, and I'll see you tomorrow. Bye.